Hello, welcome to Chapter 11, Introduction to Discounted Cash Flow Models. This is another chapter that is really exciting to me because what we're able to do in this chapter is take everything we've learned about time value of money and apply it to the evaluation of virtually any financial project. And we're going to be doing that with methods that use time value called discounted cash flow methods. So as usual, without any further ado, let's jump right in. So we've already learned, as we've talked about several times, a project evaluation method called the balance sheet review method. And we all know how that works. You start with our GAAP assets, we morph them into market values or replacement values, and we add any market brand value or something like that that has not been included previously, subtract our liabilities, et cetera, et cetera. And the problems that we've seen with that are that, first of all, we need a balance sheet. Not all projects have balance sheets. And secondly, it's very difficult, in most cases, not all cases, to estimate the true market value of the assets on the balance sheet and assets that aren't even on the balance sheet, like brand value. And finally, with this, we're always assuming the future looks like the past and there's no enfranchised growth and things like that. So, as I've alluded to previously, that motivates us to try and find other methods we can use to evaluate financial projects. The nice thing is that we can evaluate any project if we look at its time normalized cash flows. These are what I mean by time normalized is the present value equivalent of each project's cash flow. So we have to remember the time value of money, and we have to remember, well, this cash flow happens here in a year, but what's its equivalent at t equals 0? And we use our PV formulas to make that translation. So using these time normalized cash flows and an understanding of how risky a given project is, we're going to be able to evaluate any project that we want. And when we use this approach, these methods are called discounted cash flow methods. And I think on that note, I'm going to pop out visually and I'll put in Excel and I'll keep going. Okay. There are three important discounted cash flow methods. The first is net present value, and the second is our benefit cost ratio, and the third one is our internal rate of return method. We're going to have to understand all three of these to see how they work and to see what their limitations are and that kind of thing. But some key points for all of these methods: we always want to be sure to evaluate a project for one participant at a time. So definitely don't mix something like a sponsor, a bank lender, a building owner. We want to pick one of those players and evaluate the project from their perspective completely. And we're only going to consider for this project cash flows in and out for the participant that we've chosen to analyze for. Okay, so if there is the mother of all mountains of cash sitting in this project, it's not going to affect us. We're only going to consider cash flows in and out of this project to and from the participant we've chosen to analyze. And now, for the first time in time value of money, we're always going to be using a proper sign convention for all of our cash flows in all our equations and on all our cash flow diagrams. So we're not going to be anymore saying, oh, okay, well, the algebraic signs might be wrong, but we're going to use common sense to suss out what's going on. Now we're always going to use a proper algebraic sign convention. Okay, and that's true for all three of these DCF methods. And also, we're going to choose to evaluate all the projects that we look at t equals 0. Okay, and what that means is we want to discount all of those future cash flows back to time t0. Okay, so these are our key points for all three of these methods. And we have some key assumptions that we need to apply to use these models, these discounted cash flow valuation models or methods. So for now, let's consider all of our projects are independent, and also let's assume we have an unlimited budget. In addition to that, we're going to have to assume all of the marketplace and investor implications that I've covered previously. So I covered some of those in chapter 8 and some more in chapters 9 and 10. There was one page that just had this horrific list of all the assumptions needed for our models. That horrific list still applies. Plus, we have independent projects. Plus, we're assuming an unlimited budget. So alternate to the independent project's unlimited budget assumptions, we could consider mutually exclusive projects or projects with limited budget, which is the same as capital rationing. And we will do both of these things in the next chapter. All right, so let's march through our methods one at a time here, and let's start with the Npv method and see what it is and how it works, okay? So the Npv method for evaluating a project first says, as is the case with all these methods, consider just one participant, and then for that participant, we want to estimate all of her cash flows for the project. And again, now we're going to be using a proper algebraic sign convention. And next step, once we've estimated her future cash flows for this project, we want to normalize these cash flows to t equals 0. How do we do that? We take the present value of each one individually, just like we've been doing, and we want to be careful now to include all cash flows, including any at t equals 0. So this is a little bit different than what we were doing in chapter 8. In chapter 8, we were considering only the future cash flows and getting the PV of those. So in this chapter, we're also going to include any cash flow that happens at t equal 0, okay? And once we do that, once we've estimated this participant's cash flows for this project, and we've normalized them all back to t equal 0, now they're comparable on an apples to apples basis. That's why we had to discount them all back to t equals 0, because now they're on an apples to apples basis and we can compare them. How are we going to compare them? We're going to simply add them all up. So discount first, then add. That's always our rule, right? Discount first, then add. Okay, and now, since everything is normalized, if the sum of her beautiful normalized cash flows for this project is greater than 0, the meaning of that is that she estimates she's going to get more normalized cash out of the project than she puts in. So that's going to be a very helpful thing, i.e., if that's the case, if she gets more time normalized cash out of the project than she puts in, then she should go ahead with the project. And if the sum of her normalized discounted cash flows is less than 0, she should pass on this project and not worry about it. Okay, so mathematically, how are we going to set up this Npv method? Well, we have to start with a definition of the net present value. So the net present value of a project is defined to be the present value of each cash flow for this project, for this participant, including anything she pays or receives at any time, including now time t equal 0. Again, a little bit different than what we were doing in chapter 8. So with that definition, we can now write mathematically what we call the Npv formula or the Npv equation, depending on who you're talking to, okay? And it looks like this. It says the Npv of a project is equal to the sum of the individually discounted cash flows. So you see the way this sum is working. For cash flow I, first discount it, do that to every stinking cash flow, then after you've discounted them all, add them up, okay? So now we have the subscript here for I, the index rather, for I, has changed a little bit. It used to be from 1 to the number of future cash flows. Now it starts at 0 to the total number of cash flows for this participant in this project. And as has always been the case, Ti is the time of cash flow I. Let's make sure we've got everything here. Like I said, the index starts at 0, not 1. And the other thing that we might want to say here to reinforce is that we are going to be using a proper algebraic sign convention where cash inflows are going to get a positive sign and a cash outflow is going to get a negative sign. So for a simple case, I'll present quickly another way to think about this. So let's say we were paying today for a stream of future cash flows as illustrated here. Okay, so we have something like this where CF0 could be the price that we're paying for a bond, and these are the contractual cash flows that were promised from the bond contract. So we could get the NPV for the bond buyer for this contract, applying our NPV formula here. And if we do that in this case with these three cash flows, it's going to look like this for this example. Okay, so here's our minus CF0, right? Always a proper algebraic sign convention now. That's negative. That's the cash outflow that we pay to get the contract, which hopefully is going to get us these future cash flows. Okay, and then we take future cash flow 1, discount it back to its equivalent at t equals 0. Same thing with cash flow 2, same thing with cash flow 3. Bring them all back to their equivalent at t equals 0. Now everything is on an apples to apples basis. And I can just rewrite this a little bit here by putting brackets around all the future cash flows that our participant is going to get here, group those all together, and subtract from that the cash flow she has to pay at t equals 0. So if we organize things in that way, the NPV can be thought of here as the present value of the future cash flows that are promised by the contract minus today's purchase price. So that helps give us a nice qualitative understanding of what's going on here. And with that understanding, we can say we'd want to invest in this project if the present value of the future cash flows is greater than today's purchase price. And if that's not true, then probably we don't want to invest. So we've got our NPV method, and we have this great equation that we're going to use to compute the NPV of a project. But we need to think a little bit about what cash flows exactly should we be putting in here and what discount rate should we be putting in here in light of our discussion about risk in the last two chapters. So for cash flows, we always want to use, just like we did in the past two chapters, we want to use our project risk specific expected value cash flows. So for example, this is very similar to something that we did in the last chapter. We could say cash flow 1 is what's contractually promised. It's $10. It's what we're going to get if the project goes perfectly. We assign, after a lot of work, after maybe 2 days worth of work, we say, we think there's a 95% probability of that happening. Okay, and on the other hand, we think there's a 5% probability of getting 50% of that. If there is a problem with stupid managers, if there's mismanagement, we believe we'll only get $5, but we do assign that a very low probability. So what would we want to use as our project risk specific expected value cash flow for cash flow 1? We would want to say 95% times 10 plus 5% times 5. And if you work that out, check to make sure that you agree with me, but you get 975. So we'd say on average, over the long haul, we keep repeating projects like this 100 times, 1,000 times, 10,000 times. 95% of the time we get 10, 5% of the time here we get 5. So on average, over the long haul, we get 9.75. So what are we going to do with our discount rates? What do we want to plug in for R here? Well, Happily, we thought about that a lot in the last chapter, and what we always want to use for our discount rates are our opportunity costs of capital, which, as we know, can be described as either ROCC for our opportunity cost of capital or RM for our market or our industry. Either one is fine. They mean the same thing as far as we're concerned in this chapter. So now that we know the quantities to use here, our project risk-specific expected value cash flows, and our opportunity cost of capital for our discount rate, we can rewrite the NPV equation like this, where now the cash flows here are our project risk-adjusted cash flows, and instead of putting a generic discount rate R in there, let's go ahead and put in our OCC for opportunity cost of capital. Otherwise, the NPV equation is unchanged here. So this is the way we're going to be using it for the rest of the chapter and the rest of the term, and for those of you going on in finance, for the rest of your life in finance. So there are two important properties of the NPV formula. So the first one is that NPVs of our opportunity cost investments, as we learned them in the last chapter, are always equal to 0. So let's see how this works. So let's say our investing mission in life is that we invest in very low risk short-term opportunities, say about 1 year, okay? And then we know the opportunity cost of capital using our opportunity cost of capital model is going to be the known interest rate for a diversified set of alternative projects with similar risks. So what would we find in this case? There are several things we could do. And one would be we could go out to a place like bankrate.com where there are a lot of CDs on offer, and we could just pick 100 and short-term 1-year CDs and find that, take the average promised compound interest rate for those CDs, find that to be 5%, and we could look up the average price of the CDs, which is usually right around 100. So we'd find something like 100, and that would be fine. Another thing that we could do is we could be a little lazier and go to the Mint Exchange Traded Fund, which, as we learned in the last chapter, holds many short-term CDs and treasury bonds. And we could literally look up on the site for the Mint ETF, look up at PIMCO's website, the purveyor of this exchange traded fund, what their future yield rate is, discount rate, yield to maturity is for this. And they publish this frequently, and let's say we found 5%. So either of those would be fine. We could construct this diversified portfolio ourselves, looking at CDs at bankrate.com, or we could simply pick an ETF that's already done a lot of that for us. Okay, so in this case, our opportunity cost investment is going to be buy a portfolio of the CDs or buy shares of the Mint ETF. In either case, we've found from our research that those have a discount rate, yield rate of 5%, okay, as found by looking these up. Okay, and so the NPV of these investments is going to be found by just plugging into our NPV equation here, okay? So if we bought, we'd pay 100 here, okay? And then we would get what, after a year, these are for 1-year investments, we would get 105 divided by 1.05 because our opportunity cost of capital is 5%, okay, raised to the 1, okay, and that is equal to, I think, what, minus 100 plus 100 when you work all this out, and that's equal to 0.0, okay. And let me just put in a little bit of the algebra for this guy. So this is going to be CF0 plus CF1 divided by 1 plus ROCC raised to the 1. Okay, so that's where I got that from. Okay, so how can we think about this qualitatively? Okay, in this case, what we've seen up here with the algebra done for us and plugging in the numbers is that the present value of the cost of the cash flows, that would be our minus 100, that would be to buy the portfolio of CDs right now at 100, okay? That's equal to the present value of our income cash flows, the cash flows where we get money back. So here's our income cash flow, and here's our discounting of that. And what we find is this one is equal to, in magnitude, this one. So we add them up algebraically and we get 0. Second important property of the NPV method is that if we find mission-fitting investments with NPV greater than 0, we should make them. And that follows directly from property A, okay? If we put our money into an opportunity cost investment, we're going to do as well as our opportunity cost investment. But if we find something with an NPV that's bigger than that, it's implying we expect to do better. So we should go ahead and invest whenever we find the NPV of a project is greater than 0, okay? And that gives us a great rule for applying the NPV formula, which is simply going to be invest in a potential project if the NPV is greater than 0. If it's less than or equal to 0, don't bother. Okay, just what could we do? We could put the money we have into our opportunity cost investment, and that would be great. So what are our steps for using the NPV evaluation method? So here's a little recipe showing step by step how we apply this. So the first thing we're going to have to do to use the NPV method is to know what our investment mission is. We have to define it. We have to be rigorous about our investment mission. So for our short-term low-risk investor that we talked about a lot in the last chapter, this would become, our mission statement would be, we invest in guaranteed return, one-year opportunities where the opportunities are strong, okay? So similar to something like US government guarantees, strong guarantees. Okay, so that's number one step to apply the NPV method, okay? And second step is we've got to go out, just like we did in the last chapter, and find an opportunity cost investment and get our opportunity cost of capital from this, exactly like we did in the last chapter. So once again, for our short-term, low-risk investor, her opportunity cost investment is going to be a set of many one-year CDs that she found out at bankrate.com or shares of the Mint ETF, and her opportunity cost of capital is going to be the average of the interest rates shown on the CDs, at bankrate.com, or the published interest rate of the Mint as published by PIMCO, and we saw how that worked in the last chapter. So we know our mission, we've found our associated opportunity cost investment and our associated opportunity cost of capital. That's step 1 and step 2. And step 3 is now we go looking. We go looking around the world for projects with similar riskiness. These are projects that fit our mission statement, right? Or another way to say this, projects in our investment value, something like that. I can't spell in English, let alone French, but in our investment galaxy, in our investment milieu, you get the idea. We have to have similar riskiness. Otherwise, they don't fit our mission. They're not in our milieu, okay? So once we've got this potential project, then we're ready to determine its cash flows, and we want those to be project risk adjusted. And once we've got our project risk adjusted cash flows, we already have our opportunity cost of capital, and we can go ahead and solve for the NPV of this project using our Npv formula here, with again our opportunity cost of capital here, and here are project risk adjusted cash flows. And then we apply this simple NPV rule. If the NPV is greater than 0, we want to go ahead and invest. And if the NPV is less than or equal to 0, don't go ahead. And I put equal 0 down here. Why? Because it's so easy. We can always invest more money in our opportunity cost investment. That's simple. So if a project is right on the borderline, if the NPV is equal to 0, just do the simplest thing. Just invest in our opportunity cost investment.